Let's talk about a business application that comes up in calculus. So let's say the revenue in thousands of dollars from producing X units of an item is R of X, which is 20 times X minus 0.005 times X squared, which means if you wanted to say find the revenue or how much you made in producing 2 units, you do 20 times 2 minus 0.005 times 2 squared, and that would tell you how much you made in producing that many or 2 units. So let's find the average rate of change of revenue when production is increased from 100 to 101 units in a business. You want to find that sweet spot of essentially how many units should I produce to maximize my profit. So we're essentially trying to figure out if we produce one more unit, do we gain money or do we lose money in general. So average rate of change is going to look like R of 101 minus R of 100 divided by 101 minus 100. You can essentially see that it's the slope of the line between the 2 points where x is equal to 100 and x is equal to 101. So revenue of 101 is 20 times 101 minus 0.005 times 101 squared. And then we'll subtract off revenue at 100 units. So I'll open up some parentheses. 20 times 100 minus 0.005 times 100 squared, all divided by 101 minus 100 is just 1. So that'll be the last time I write the denominator in. 20 times 101, 2020, minus 0.005 times 10,201 is 101 squared, minus 20 times 100 gives me 2,000, and then minus gives me plus 0.005 times 100 squared is 10,000. So for some of these numbers, I used a calculator ahead of time to figure out what they are in business. A lot of times or other applications, the numbers aren't quite that nice. So you would want a calculator in real life in general. So 20,000 minus 2,000 gives me 20 minus 0.005 times 10,201 was 51.005, and then 0.005 times 10,000 was plus 50, which gives me 18.995 once you do that calculation, which means changing from 100 units of production to 101 units of production means we gained $18,995 in our revenue. So whatever this business is, they're making some big ticket items because they get in about $18,995 more by producing one more unit when they're moving from 100 units to 101 units. That may be very, very, very different if they're moving between different numbers of units in general. So again, this was in thousands, so we moved that decimal 3 places to the right to get the actual value. All right, that's average rate. In calculus, we often want to know the instantaneous rate of change. So similar question, we've just changed it to instantaneous rate of change with respect to the number of items produced, which again, in our case is X, when 100 units are produced. So what that's going to look like is the limit as H approaches 0 of R of 100 plus H minus R of 100 all divided by H. This is instantaneous. It's the slope of that tangent line to the curve right at X is equal to 100 instead of using that slope of the line between 2 points, 100 and 101. So let's start filling these in. So this will be the limit as H approaches 0 of R of 100 plus H is going to be 20 times your X, which our X is 100 plus H, minus 0.005 times 100 plus H quantity squared. So that whole part right there is R of 100 plus H. We'll subtract off R of 100. Be careful you subtract off the whole thing, not just the first term, so open up some parentheses. 20 times 100 minus 0.005 times 100 squared, all divided by H. So let's start expanding, collecting like terms. Again, I have used a calculator ahead of time for a couple of these numbers because business applications have some interesting numbers at times. So send that 20 through. 20 times 100 plus 20 times H minus 0.005 times, and if we expand, this 100 plus h squared, we get 100 squared plus 200 times h plus h squared minus 20 times 100 if we start on this last part in the parentheses, plus 0.005 times 100 squared, all divided by h. So we'll notice that this 20 times 100 and this minus 20 times 100 cancel each other out by adding up to 0. So let's start sending through 0.005 and see what we get. This is the limit as h approaches 0 of 20h minus 0.005 times 100 squared minus 0.005 times 200h minus 0.005h squared plus 0.005 times 100 squared, all divided by h. From here we'll notice that this term and this term add up to 0 again, and then every single term we have left up in the numerator has an h in it. So let's factor out that h, because right now we're still, if you try to plug in h is equal to 0, same with back at the beginning, I didn't mention that, but back at the beginning, and even here, if we plug in h equals 0, I get 0, 0, 0, which gives me a 0, all divided by 0, and 0 over 0 is an indeterminate form, so we're doing some algebra to try to get it so it's not 0, 0. So if I factor out an h from the numerator, I'm left with 20 from that first term, minus 0.005 times 200 from the next term, and minus 0.005 times h from the last one. That didn't cancel out, divided by h. So now I have an h over h, which is just 1, so this looks like the limit as h approaches 0 of 20 minus 0.005 times 200 minus 0.005 times h, which, as h approaches 0, this term is 0. The first two terms are just constants, so when you do the algebra with those, you're left with 20 minus 0.005 times 200, which is equal to 19. Which means the instantaneous rate of change, that was in thousands, so 19 is $19,000. This thing is called marginal revenue at x equals 100. What that is it's an instantaneous rate of change of the revenue function, which is essentially, if you're going to produce, more, you're going to gain $19,000 more per unit, roughly. Depending on the textbook or the company you're working with, they either call this instantaneous rate of change marginal revenue, or other companies will use this average rate of change for their marginal revenue, which is essentially the revenue gained by producing one more unit. So I wanted to introduce you to both. The nice thing about the instantaneous one is it's calculus based. We're going to have a much easier time in the future trying to find things like maximum revenue so you can maximize your revenue. To do that, we'll have to get a couple other differentiation rules to make our lives a bit easier, but that's where we're headed.